Hi, let's continue solving our question number 7th, the part B. Write the k nearest neighbors algorithm using the Euclidean distances. So let me just quickly present. Let us start with one of the simplest yet surprisingly powerful algorithms in machine learning, KNN. Imagine that we want to classify a new data point, but instead of training a complex model, we simply look around at the closest neighbor, almost like asking nearby people for advice. That is the philosophy of KNN. Right. Step one, we choose the value of k. How many neighbors will we consider? Step two is measure the similarity between the new data points and every data point in the training set. We typically use Euclidean distance, defined as the square root of the sum of differences between corresponding features. Step three is to identify the k smallest distances. These represent the nearest neighbors. Step 4 is we are performing classification. We assign the most common class among those neighbors. If we are performing regression, we take the average of their values, and that's it. KNN is a memory based, lazy, and intuitive solution. Instead of it basically relies on geometry of the data set, and that's how we get it. For implementing it with the Euclidean distances formula, we need to follow this specific formula, that is the square of the summation of the corresponding features differences squared, and that would be it. Now let's move on to the question number 8, compare decision trees, random forests, and boosting, highlighting strengths, weaknesses of each. So let's move on to that. We compare three most influential modeling strategies. So decision trees are straightforward and interpretable. They mimic human decision making. At each node, we ask a question that splits the data into two, and their strength lies in their transparency and their ability to model nonlinear relationships effortlessly. But their weakness is overfitting. A single tree can often memorize the training data and make it unstable and sensitive to noise. Like a remedy to this instability is random forest. Instead of relying on one single tree, we train many trees on a random subset of the data, and the random subsets of these features, the forest aggregates their predictions dramatically, reducing the variance. However, the ensemble approach makes the interpretation a little bit more tricky and difficult. Boosting takes a different strategy. Rather than building decision trees independently, it builds them sequentially. Each new tree tries to correct the mistakes of the previous ones. This produces an extremely strong predictive performance and is widely used in competitions. Yet, in it is sensitive to outliers and many and may require like careful tuning, right? So the training speed is the fastest in decision trees. It is moderate in random forest, and it is quite slow in boosting algorithms. Interpretability is the easiest in decision trees. It is limited in random forest due to ensemble learning, and it is very limited in boosting. Let's proceed to the next question, that is explain the architecture and components of Hadoop, HDFS, Yarn, MapReduce, or describe the Spark and its advantages over MapReduce. So let's proceed to that. uh, Hadoop's architecture, distributed computing at scale. HDFS, or the Hadoop Distributed File System, provides resilient, fault-tolerant systems that are required for storage. Large files are split across multiple data nodes, while the same nodes hold the metadata. This architecture enables massive parallel storage on inexpensive hardware, and Yarn acts as the resource manager and job scheduler of the Hadoop ecosystem. It determines which tasks run when, where and how the clusters are resourced and allocated. MapReduce is the Hadoop's original processing framework. Map phase basically transforms the input data into key value pairs and reduces the reduce phase aggregates them. It is a reliable and scalable method, but it inherently batch oriented and slow for iterative workloads. Option B, we can also look at Sparks and its advantages. So alternatively, modern pipelines often prefer Apache Spark. Apache Spark is basically Spark performs multiple computations in memory rather than writing to disk after every operation. It uses resilient distributed data sets known as RDDs and provides higher level APIs such as data frames. So, Spark usually outperforms MapReduce. The advantages are substantial because Spark is dramatically faster, supports iterative algorithms, accommodates streaming workloads, and often offer built-in libraries for machine learning and graph processing. Where MapReduce struggles with multi-step pipelines, Spark thrives. That would be it for this video. We shall solve the question number 9 in the next one. Thank you.